Hey guys, welcome back to the Biomechanics 1 video series. In this specific one, we're going to look at some worked examples that involve concepts of torque. I'm going to give you guys three worked examples. The first one starts off pretty straightforward. We look at a table with a book on a table, and in essence we want to find out how much weight is being supported by each specific leg. The second one that we want to look at it's a fairly classic example. You've got some weights on a bar that is stacked on a squat rack. So often what you see is the gym guys take, weights off the one side and this whole system comes crashing down. So in essence what we want to be able to do is determine what is the safe amount of load that you can put on one side without this system being destabilized and creating a net moment around a specific pivot point. So that's a little bit more involved, but not much more than the previous one. And then the final one is a gymnastics example. So you've got a person performing the iron cross, and in essence you want to determine how much weight is being supported by each arm. And in essence, what are the implications of the muscles in the specific scenario. Okay, great. So without further ado, let's start with this one. So we've got a book on the table and its weight is approximately 20 newtons, and in this scenario over here the weight of the table is approximately 100 newtons. I'm going to label this leg over here A and this leg over here B. So we've got these masses. This is the center of mass of the table, and it is a certain distance from each leg. You've got the center of mass of the book, and it is a certain distance from each leg, knowing that the legs are separated by 4 meters. So in essence, if I want to firstly find out how much weight is being supported by, let's start with leg B. So what is the load that leg B has to be able to support in this specific system? Just thinking about it logically, if there's more mass being shifted towards the one leg, we would, I guess, logically assume that leg A should carry a greater load than leg B. But let's see if the maths behind all of that kind of verifies that. Okay, so in essence, if I want to find out how much load is being supported by leg B, I could think of this whole system being pivoted around leg A. So let's say, for example, that was my fulcrum, and in essence, this whole system, if I think of just about this top slab of the table, is then pivoting around that point, and therefore has to be counteracted by leg B. In other words, since these center of masses are a certain distance from this fulcrum, they would cause a net anti-clockwise rotation. The only way that this net anti-clockwise rotation is prevented is by the force being supplied by leg B. Right? It has to counteract that with a clockwise rotation. So in essence, if I'm then trying to determine what the force is that leg B has to supply, I would be able to calculate it as follows. So the moment about point A is equal to the sum of all the anti-clockwise moments plus the sum of all the clockwise moments, and all of that has to basically sum to 0. Since there's no net rotation happening, there's static equilibrium in this specific scenario. So if I start unpacking the sum of these anti-clockwise moments, I have the 20 newtons supplied by this book over here, and its distance from the axis of rotation is 1 meter. Plus, I have the center of mass of the table, which is 100 newtons, and it is a distance of 2 meters from the axis of rotation. Plus, then I have this negative force B times its distance, which is 4 meters from the axis of rotation. The reason it's a negative is because it is going to initiate a clockwise rotation, and all clockwise rotations are described with a negative value. Remember, we have to set up our convention as follows. So anything moving to the right and up is positive, and your anti-clockwise moments are positive, and all of that has to equal 0. So in essence here I've got 20 Newton meters plus 200 Newton meters must equal FB times 4. So therefore FB is equal to 220 divided by 4, and that's Newton meters divided by 4 meters, and that's going to give me a final value of 55 newtons. Alright, so leg B has to supply 55 newtons, or is taking 55 newtons in the specific scenario. If I look at the moments about point B, so in other words, now I'm trying to find out how much weight is being supported by leg B, and I treat this as the pivot point. Therefore, now these two masses would be rotating around this fulcrum, and therefore would be creating a clockwise moment, and therefore leg A would have to initiate an anti-clockwise moment in order to keep equilibrium. So again, it's the sum of all anti-clockwise moments plus the sum of all clockwise moments have to submit to 0 in order to maintain static equilibrium. So let's start off with these clockwise moments. So again, clockwise moments are negative, so it'd be negative, and now remember, if I'm looking at this book over here, its center of mass is now not 1 meter from the axis of rotation, it is 3 meters from the axis of rotation. So I have to take this 20 newtons and multiply it by the 3 meters plus the center of mass, which is 100 newtons, multiplied by its distance, which is still 2 meters from that leg, plus the distance that this leg is, which is now force A from the axis of rotation, which is leg B. So therefore, same way as we had earlier, force about A is equal to 20 times 3, which is 60, and 100 times 2, which is 200. So I've got 260 divided by 4, which is 65 newtons. Okay, and that's providing a clockwise moment. Sorry, I must not forget my negative signs. So that's just going to dictate the direction of force application. Nope, sorry, this is going to be a positive value. Reason being, remember, this is all going to equal 0. So if I take all of these values, which are negative, over to that side, I'm going to get a positive 260 divided by 4. So it's going to give me positive 65, which is nice to see because of the fact that, remember, this force is being directed upwards, okay, as by our convention. So I've got 65 newtons of force. Again, this value is higher than the 55 being supported by leg B. And the other thing that's nice to see is if I've got this 20 newtons down and this 100 newtons down, those are the only masses acting downwards, correct? So in essence, what these legs have to counteract is an equal and opposite load, right? So it's being directed downwards with 120 newtons, and therefore I should see a total of 120 newtons acting upwards, which is what I see when I sum FA plus FB, which also gives me 120 newtons upwards. So your 65 plus 55 gives me 120, which counteracts this 120 acting downwards. So therefore, the sum of forces is equal to 0, and the sum of moments equals to 0, which is what we need in order to have static equilibrium. So everything kind of checks out. Perfect. Alright, see you guys next time.